Okay, hello, welcome to the second set of examples so that you can then complete exercise 3A in your FM1 textbooks. So example 5 is quite a straightforward one, but it puts things in context. So it's using your knowledge from your normal A-level maths here to create your force diagram, and then obviously adding Hooke's law to the mix to be able to answer the questions that we're given in FM1. So here we've got an elastic string of natural length 2 meters and modulus of elasticity 98 newtons. One end of the string, as you can see, is attached to a fixed point O, and the other end is attached to a particle P of mass 4 kilograms. The particle is held in equilibrium by a horizontal force of 28 newtons. It's obviously got to be in that direction to counteract the tension in our string, with OP making an angle of theta with the vertical there. So again, just put the theta value in there to the vertical as well, and the only weight we need to add there is the weight of the particle for 4g. Now again, we're told it's held in equilibrium, so we can resolve in each direction. So first of all, if I resolve horizontally, we've got that 28 is going to equal t sine theta, and if we resolve vertically, we have that t cos theta equals 4g. So straight away we can find out our angle by dividing our two equations. Obviously if I wrote that as 4g equals t cos theta, that might have been a little bit easier, but essentially here, if we do 1 divided by 2, you can see that we have t sine theta over t cos theta is going to equal 28 divided by 4g. So therefore tan theta is going to equal 28 over 4g, and we end up with theta equaling 36 degrees to two significant figures. So we've answered part A. And then part B, to find the extension in the string. Now we know that theta is 36 degrees. I would still keep the real value in there when we find out t from either equation 1 or 2. So if we use equation 1, we've got t is going to equal 28 divided by the sine of theta. And we also know, using Hooke's law, that that is going to equal lambda, which is 98x divided by 2. So therefore, if we multiply by 2 and divide by 98 to what we have for our tension, we have the value that x is going to equal 0.98 meters to two significant figures. But this is why I said you've got to be very careful. The question actually asks for the length of OP. So the length of OP, so just always make sure at the end that you've actually answered the question, because it'd be such a shame to lose a silly mark having done all of the hard work. So it's going to be 2 plus 0.98 meters. So the distance from O to P is the natural length plus their extension, which is 2.98 meters. And then moving on to example 6, here we have two identical elastic springs. So it's all about the distances within here, a little bit like one of the examples in our previous video. Rather than having two unknowns, I'll create one unknown by using this gap area here. Sorry, a gap area, gap distance, I should say. So in example 6, we've got two springs, PQ and QR. Each have natural length L, okay, and modulus of elasticity of 2 mg. So they both have natural length L and modulus of elasticity 2 mg. So they're attached to, joined together at Q again, okay, and their other ends, P and R, are attached to fixed points where the distance is 4L vertically between those 2 points P and R. So our mass here, if I just use a different colour for the equations again, so it's a mass of M, so we've got a weight of mg, and then we've got tension in spring 1, so if I put tension of PQ, and then we've also got the tension of QR. Now it's worth noting here that the tension of PQ is obviously going to be trying to pull the particle back up because it's extended. if this became such a, well, let's just say the weight was heavy enough that this spring ended up actually being compressed, then what we would have is that value would end up being a negative. So in principle, you don't need to worry about that. But obviously, if that was big enough, then that would cause that to be negative. In other words, that spring would be compressed and therefore providing a thrust. But that will come out within our equations anyway. So if that ended up being negative, that would become clear as we work through the question itself. So what we have here, first of all, by resolving vertically, we know that, I forgot all this, might be easier to actually call these T1 and T2 in future reference, but I'll stick with what I've got there. So the tension in PQ is going to equal mg plus the tension in QR. And then using our Hooke's law equations, we have that the tension in PQ is going to equal. Now, what we've got here is our natural lengths of L and L. So that leaves a gap here. Just use a red pen to show you this clearly. That gap there, therefore, is going to be 2L. So if I call that extension X, then this one is going to be 2L minus X. So again, it saves us having two unknowns, X and Y, say, and just having one unknown by thinking about the distance there. So L and L leaves a gap of 2L. So if we call that extension X, then that will be 2L minus X. So the tension in PQ is going to equal lambda, which is 2mg, X over L. And the tension in QR is going to equal 2mg, because they're both the same modulus of elasticity. They're both the same natural length. So we're going to have 2L minus X over L. So if we put those into our equation above, we've got the tension in PQ, so 2mg X over L is going to equal mg plus the tension in QR, which is 2mg over L multiplied by 2L minus X. You can see that the mg's all cancel out, remembering that becomes 1. So then we're going to have 2x over L is going to equal 1 plus 2 over L lots of 2L minus X. It's probably simpler then to times everything by L. So we've got 2x is going to equal L, so 1 times L plus 4L minus 2x, and we end up with 4x equals 5L. So we have the extension in the spring is 5L over 4. Now, once again, the question has asked us to find the distance of the particle below P. So the actual answer to our question is going to be L plus 5L over 4. I'll just put the answer here as we're running out of space. So the answer to the question is going to be L plus 5L over 4, which equals 9L over 4. And that's the distance of P to Q. Okay, and the final example now, which we'll look at before you can now complete all of exercise 3A. We have one end A of a light elastic string AB of natural length 0.6 meters and modulus of elasticity 10 newtons is fixed to a point on a fixed rough plane inclined at an angle of theta to the horizontal, where sine theta equals 4/5. So again, we've talked about this a number of times before in our normal applied videos as well. So we've got a 3, 4, 5 Pythagorean triple. So wherever we need it, that means cos theta will be 3/5 and tan theta would be 4/3. And we're told that a ball of mass 3 kilograms is attached to the end B. So we have a weight there, first of all, of 3g. The coefficient of friction mu between the ball and the plane is 1/3, and the ball rests in limiting equilibrium on the point of sliding down the plane. So if it's on the point of sliding down, then our friction force is going to be trying to prevent motion, and we are told it's in limiting equilibrium, so we know the friction force is at maximum. So we can write that as mu r immediately, which is going to be 1/3 of r, because we're told the coefficient of friction is 1/3. And we obviously have our reaction force there and the tension in our string. So we've got to find out the tension in the string and the length of the string as well. So it's the same two equations. I mean, this is the key, isn't it? You start to see that we are going to resolve our forces because everything's in equilibrium. So we're going to resolve when we have a plane parallel to the plane at right angles to the plane. And then our third equation, which is the essential thing that we're adding here in Further Mechanics 1, is using Hooke's law to find the tension in the string. But you should start seeing that pattern approaching. Even if you find these questions difficult to start with, we're essentially doing exactly the same thing time and time again. So if we resolve, first of all, down the plane, we're going to have that 3g sine theta is going to equal the tension in the string plus mu r, which is 1/3 of r. If we resolve at right angles to the plane, we've got that r is going to equal 3g cos theta. So that replaces r straight away. And then finally, using Hooke's law, we know that the tension in the string is going to equal lambda, which is 10 times x over the natural length of 0.6. So we replace t here with t there, we replace r, and we'll be able to find out the extension in the string straight away. So again, it doesn't matter which order you do it in, we also need to find the tension in the string, so we could do that straight away, I guess, first of all. So in fact, we'll do that first. So the tension is going to equal 3g sine theta, which we were told was 4/5, minus 1/3 of r, which we know is 3g times the cos of theta. And if we put those together, we've got 12g over 5 minus 9g over 15, which is going to give us a value of t as 9g over 5, or 17.6 newtons to 3 significant figures. And then once we have the tension, we know that the tension, so 9g over 5, is going to equal 10 lots of x divided by 0.6. And if we rearrange that equation there, we're going to get that x is 1.06 meters to 3 significant figures. Now again, I'm just checking on the question. It asks us to find the length of the string. So the length of the string is going to be the natural length, which is 0.6, plus the extension, which is going to be 1.66 meters. Again, make sure you actually answer the question. Now for the final part of the question, so part B, it's saying that if mu was greater than 1/3, and it emphasizes here without doing any further calculation. So you're just thinking about what's going to happen if mu is greater than 1/3. So that means that the friction force is going to be greater, as mu is greater than 1/3. That means that if the friction force is greater, then tension would be less, as F is greater. So just thinking logically, so if mu is greater, that means the friction force is greater, which reduces the tension in the string. So therefore X is going to be less than 1.06 meters, as lambda and the natural length are constant. So if tension is reduced, if I just write the equation for Hooke's law there, they are constant. So if tension is less, then you can see that the extension in the string is also going to be less. So when it says without further calculation, that is what you're expected to do. So that's it for the 2 videos looking at all of these different sorts of examples. Exercise 3A is quite challenging. There's lots of different questions that you're given, so 11 in all. That should be enough for you to be able to now work through all of those. And I'll see you again for the next exercises, the videos for the next exercises shortly.